Hello. Today we're going to talk about a problem from the second Academic Excellence Workshop. So this is on the second worksheet, problem 2D. So in this problem, we've got a monk, and he's pulling some bricks up a hill. And the hill's got friction on it, and so he wants to know how, he's tired, and so he wants to know how softly he can pull on the bricks without them sliding down the hill. So we're going to find that out. So we're given the angle of the hill. This right here is theta. We're given the mass of the bricks, and we're given the coefficient of static friction. And we know we're only going to have to use static friction in here because we don't want the blocks to accelerate. So we started off by drawing a free body diagram. I've already drawn it for you. So you can just ignore the red for the moment and look at the black. We know we've got a normal force pointing normal to the surface, often in that direction. We've got the force from the monk, and it's of course pointing up the hill. We've got the static friction force, which I chose to go up the hill, and you probably understand, but I'll explain it in a minute. And then the weight force, of course, is pointing straight down. So the reason the static friction force is pointing up the hill is because we want the static friction force to be doing as much as it can for the monk in order for him to not have to pull very hard. So if it were pushing down against him, he'd have to pull really hard, but since it's pulling up for him, he gets a break. So another thing that's really important is the fact that in this case, this static friction force is going to be at its maximum value because that's going to give the monk the most of a break. So let's just go ahead and generate two equations. I've chosen this set of axes to represent this scenario. So let's go ahead and get the sum of forces in the x and the y direction for some equations. So if we sum the forces in the x direction, we get the force from the monk, call it Fmb, plus the static friction force from the ground, which we already said was going to be at its maximum value, which we know is mu sub s times the normal force between the hill and the bricks. And then we're going to have to subtract off from that the x component of the weight force. So we know that this angle right here is theta, and I would really study this picture if this doesn't make sense. But as a result, we know that the component is going to be times sine of theta. So we've got this. And we know that we don't want this to move, so I'll say it equals 0. Now we'll do the same thing in the y direction. I'll go through this a little more quickly. We've just got the normal straight up, and similarly to before, we've got mg cosine theta to describe the component of the weight force in the y direction. And that equals 0 in this case as well, because it's not accelerating. So, as a result, we know from the second equation that normal force must equal mg cosine theta in this problem. So, if we just take this and we plug it in right there, we know everything else in this equation except for the force necessary. So all we did in this problem was we said, all right, the friction force has to be at its maximum value and it has to point up the hill. And then we just wrote out two equations and we found out we just have one unknown. So if we go through this and plug in all our values, which I wrote over here, we'll get that the force required is a tiny 4.736 newtons. So the monk should not have very much trouble at all.